All right. Welcome to the second part of today's class and the second week. And I want to talk about, present you here about underground water system from the ancient period to gardens and parks in the Islamic world, which is already pointed out by previous lecture by Mr. Valentino that he described it in terms of, he called what called Arab world, which is pretty much from the perspective from Europeans. But larger than Arab world is the Islamic world, in which in the height of their civilization, we could say maybe roughly from 600 AD to 1500, was most, we would consider that they have most developed use of water for a various reason in the sense of both technological and cultural way. So we begin. Just a second. Why is this not moving forward? Hold on a second. I'm such a klutz with the computer. Why am I having so much problem here? Okay, there we go. Okay, so I will begin with an area that is near Italy, that Naples, that Mr. Valentino was talking about. And I've actually put down my some of the things that I want to read to you right on the screen that would be more useful for you after the lecture as well. And this is an area called Dalmatia, which is across east of Italy, across the Adriatic Sea. And Dalmatia was a separate entity, now belongs to mostly to a nation called Croatia, which was part of the ex-Yugoslavia. Okay, and in this area, they were especially very, let's say, very beautiful, or one of the tourist hotspots in Europe. And because it has so many islands, but at the same time, it has all these rivers that are indicated in this map. And they had also had abundance of springs and aquifer, and which gave a very important source to their social, economical, and ecological values. And the existence of them was crucial for the permanent settlement and development of urban centers on the Croatian littoral, as well as Roman settlements. In fact, before, as Mr. Valentino explained in the history of Naples, this area was also first settled by Greeks. And then later it was from the 4th century to 3rd century BC. And then the Roman Empire followed soon after. And I will send you the bibliography of this. Underground Aqueduct Handbook is incredible resource, stupendous, 600 pages long, which you can get downloaded from your favorite website. And so again, the Roman, once the Roman port, Roman settlements began, I want to focus on a couple of areas here. And the Roman port of Navalia was situated in a bay in the northwest of Peg Island. So that's number one. And let me see if I can get my mouse to it. Obey, sorry. My mouse doesn't work here. Okay, that's great. but you can see number 1 here on very top. And in order to supply their ships with drinking water, the Romans built a 4-kilometer long aqueduct, of which 1 kilometer was dug as tunnel in bedrock. And you will understand why that aqueduct and tunnel was necessary in order to transfer water from the source to where they need it. The Navalia aqueduct was supplied with water from Skopalia spring. It was discovered in the first half of 19th century and the beginning of 20th century. It was reused by laying water pipe into the channel. Maybe you might misunderstand that it wasn't built in the 19th century. It was built in ancient period during the Roman settlement, which could be anywhere between roughly around 2,000 years ago. But it was abandoned and rediscovered in 19th century. And then it was put into use again because it was conveniently connected to water source. So they put a new modern water pipe into the channel, okay? Water was then pumped from the spring by pumps powered by a windmill and a motor since a windmill and a motor since 1929 and electrical energy since 1949. So you can see the transition of the force that was utilized to move the water from the source to its destination, from a windmill to a motor, which I don't, the book does not indicate what kind of motor this was. But since 1949, they used electrical energy to drive the motor to push and move the water. And before then, I would have to assume that the water was moved by natural force of gravitation and siphons, okay? In other words, that there were no, let's say, should I call man-made energy, mechanical energy, or natural resource energy, and so on. So here is an illustration that shows that that some of the infrastructure or engineering or construction that was built to move the water, and one of it was an aqueduct, and that was about 3.5 kilometers from the town, the destination, with a minimum supply capacity of 100 liters per second. Now, I forgot to ask you that, do you see my, the screen of the image of this aqueducts? Thank you. Okay. So, of course, you don't know what 100 liters per second is. Well, it means 100 liter moves through an opening or the cavity or the channel or the pipe water per second, okay? But we don't really know relativity of that, and I think you would see that more later. I see some of the mistakes here on the transfer of data, that is software transition problem. At the 23rd meter of the channel, there's a double lock and beginning of second parallel channel, okay, supplying a mechanic device with water. The gravity channel of the aqueduct follows the terrain contour line. A greater part which was executed as a superficially dug channel, while its lesser part was completely cut into the rock. This means that they were mechanical devices used water to move, and perhaps that in the upper right hand, there inside there was some kind of mechanical devices that may be driven by animals or even human to move or push the water or even raise water from one level to another level. And the other thing is that when it says it followed the contour of the terrain, which means that when you follow when you follow the land, then you keep the line of movement or channel or a pipe to move the water in horizontal level rather than going up and down. In other words, it's like if you build a road that follows around the curve of the mountain, rather than in, let's say, in San Francisco, where you ignore the contour and build grid-like streets that creates something like 25, 30 degree slope angle. But the reason why you follow the contour of the land here would be to use gravitation as the power to move the water from one point to the other. And while its lesser part was, okay, because of the small level difference between spring, the source of water, and the town, in other words, they were almost similar level in elevation. Maybe, of course, town was probably lower, but not significantly. The slope of the channel was extremely gentle to the level of 0.0077 to 0.095 percentage or degree. Sorry about this typo here, but it is from transferring data to one to another. Okay, then at the same time, two important aqueducts were built, both at the end of 1st century AD during the reign of Roman Emperor Trajan. The older one is 25 miles long and was supplying water from Biba Spring near Lake Varana, and the channel is a 60 centimeter or about 24 inches wide, and the longitudinal slope is between 0.64% to 2.54%. Much higher than previous one, but still pretty gentle. On the aqueduct route, a valley of about 5 kilometers long and about 36 meters or 118 feet deep, which is significantly a deep valley, was bridged over by a siphon, which is incredible to imagine that the siphon was used without any mechanical, in other words, still remain as a natural, it's not gravitational, but a force to move the water. Now, what is the siphon? Well, I myself am not an expert on this, but it's like if you suck with, let's say you get a piece of tube and you want to suck something out of like water out. I guess a straw would be good, that if you pull with your force, then the water would come out of the cup, which is below you. After you let go of it, it still will start to pour it out, okay? So in other words, it takes water from lower ground, upper ground by the natural force of suction. The remains of siphon made of stone pipe 35 centimeter of inner diameter was found. And besides it, there was a lead pipe of inner diameter. In other words, that original was made of stone, but later that pipe was put in as a sign of improvement of the system. As a matter of fact, the water to Los Angeles, when it was brought by famous Mr. Mulholland, which famous Mulholland Drive in Los Angeles, that is named after, where is a very popular scenic route to drive your car to see the scenic view of the city below. He is famous because he brought water to Los Angeles. I believe that he opened the first aqueduct, if we call it, or maybe canal, from Owens Lake that may have been, I don't know, I can't remember, more than 250 miles north. Build canals, channels, pipes to mountains. Obviously, you have to go through Sierra Mountains, and brought into the city of Los Angeles by 1910, I believe. And that's what made the first large water channeling system that made Los Angeles city of this size today. And without that water being brought in, the Los Angeles would not be this size, or Southern California, as a matter of fact. Of course, there are many other water channels made, but that whole distance of 250, I believe, was largely made, although there was probably mechanical pumps somewhere, but was made out of gravitational force. And sometimes the pipes would rise above the horizontal level of gravity, but the force from the water preceding it would push it up the hill. So that may be a kind of what might call siphoning system. And that was all calculated and engineered. The importance was the hydrology engineering of that as well. Yeah, 미치겠다. 이 새끼 컴퓨터 이거 진짜. Okay, so you see that now here's the remains of an aqueduct built with construction of Diocletian Palace. I believe it's a Roman palace. And you can see underground that the channel of water, which was a stone channel covered with stone over it, that, as you can see during the excavation, that much of it is destroyed. And in fact, the interesting to say about it is that in spite of this condition that you see here, more than half of its original route is still in use. And this old Roman channel capacity of 470 liters per second, somewhat less than 1/3 of overall water supply to the city called Split, which is a famous tourist beautiful site in Croatia, with a population of approximately now 300,000 people. So you can imagine that even almost 2,000 years ago, that this system that they built would have served more than 100,000 people. which at that time, there were very few cities in the world that would have had population of 100,000 people. Then along the way, in fact, in the same water channeling system, an aqueduct bridge was built. And this, as you can see, is a tremendous construction and engineering, somewhat like 2,000 years ago. So we have to begin to appreciate the capability of engineering construction of ancient period, especially prolific builders like the Roman Empire. Thank God, well, maybe not thank God, but their use of slaves, even their soldiers. And here you see a basic section of and the plan of the aqueduct channel. Okay, and what you see is on the top called the plan. At the very top, what looks like a kind of a road. Well, it is. Its contour or its meandering fashion is determined by, as I have explained before, following the contour of the land. Now, when you have your phone and you're on Google Map, if you push contour, then you will see how the contours are drawn out in the map, showing a line that shows the same height of elevation. And so this would be following one of those lines with the decline of elevation from the source of water on the left side to the destination, the town of Split on the right side. And below that drawing, what looks like a mountain is actually what we call section. This in case longitudinal section, meaning that it was cut through one direction, not latitudinal section, which would have been exactly opposite direction, cutting through at 90 degrees. But it's an illustration of, if you cut the land in half, you would get something like this. So the top line is actually the top elevation along the route of the water that moves through. So you were seeing top of the land. So obviously in the middle, the highest point, we might call it a ridge of the mountain. Now this probably is compressed, so it's exaggerated, in other words, right? And the bottom is the bottom line of this section that looks like, you know, maybe I would tell you that maybe the best way to think about, imagine what a section is, would be think about your birthdays. If you're lucky enough that you have friends that brought you cakes and you cut the cake to give out to your friends. And when you cut the cake, you see the section of the cake and it would look like something like this, although it would be more flat, horizontal layers. On the top, you have these sugary cream or whatever, frost. Maybe even above that, a whipped cream, some fruit, and then different crusts. Sometimes you have different colors, chocolate, vanilla, strawberry, whatever, you know, like flavored, and maybe, you know, so you get my point. That would be a good way to imagine what a section is, okay? And so I cannot really read the illustration myself. It's too small of a print, but so I would have to take a guess that the bottom line of this section is the elevation of water, or the bottom of the water, or the top of the water channel. And you can see that it gradually inclines downward from the source to the town of Split, now a city of Split. And then on the top, you see another kind of line that follows the bottom line. I would have to take the guess that would be the top of, let's say, underground tunnel that was built. And in other words, the ceiling of the tunnel, okay? Or the other guess would be that that would be, now let's leave it at that, okay? But you get my point, right? Okay. So then if we read the direction, here is that 1.7 kilometers of 9.5 kilometer of the aqueduct channel was below ground and in 3 separate tunnels. One is 287 meters long and 3,000 meters from spring and so on. Sorry, I didn't convert it, but there's too many things to convert here into feet and miles. But 287 meter would be about 1,000 feet or more, okay? There were 32 vertical shafts, and those are the vertical lines that you see on the section. Why were there shafts? Because they dig shaft to go down to dig tunnels and to bring the debris that you excavate out to make a hole up to the shaft, up to the ground. You have to take them out, right, to make a hole. They also gave air so that people working down below would have air so they wouldn't, let's say, die, right? And that they could keep working. And there's also another reason why that there were so many shafts built, not because of those 2 reasons I gave you before, because these shafts allowed that people to dig holes at multiple spaces at the same time. In other words, if there were theoretically, what did they say, 32 vertical shafts, they could dig 34 points at the same time and then going each direction or one direction or and end up meeting each other. Why was this important? Is because this allowed faster construction. Otherwise, it would have not been impossible to build such a long underground tunnels. It would have taken too long a time. Back in those days, they didn't have big machines like we do. So they could only put 2 or 3 people down maybe, at once through the shaft because there was not enough room to work for people to dig and work with rudimentary tools. So you see now that the remains of these tunnels, and there's a shaft at the bottom, a vertical shaft that you go down and you with on a maybe some kind of a basket-like contraption where you go in to go down and also to put things in it that you dig out in order to make the tunnel. So it's really not that much different from mining, except the only point is in mining was done through mostly one hole in horizontal approach, where this was done with these vertical shafts. an image at the top, you see that there is water still underneath after uh, almost 2,000 years. And much of the stones that were used to, some of the stones that were used to cut out a hole was used also to build a much more defined contour to the tunnel to direct and control the water, as well as to be able to go in and out when necessary to maintain the flow of the water from being blocked, right? So it's like today's home where if you're well, I guess something happened and we got interrupted. According to my computer, I lost internet connection. How's that? Um, are you still with me here? Oh, okay. I'm surprised that. Okay, so I would return. Thank you, Raffaele. I'm glad that I was able to get back. I can't believe how much trouble that I'm having with Zoom when I had none last quarter. Unbelievable. Okay, so now I have to turn everything back on. Hold on a second. Let me first of all make sure that I share the screen. Okay. Uh, did you hear me all the time before? Okay. Up to that point, Jessica, did you hear my audio?
I remember the last part is I think it's like the middle part of the shaft of this PowerPoint.
Uh, I'm going to stop recording now and